Here's an example we started in class. I wanted to go through this. Again, this is I had advertised this as being sort of a 131 problem in disguise. And so we're given two small spheres, each of 3 nanocoulombs, and when they hang them from strings with gravity, and here gravity is acting straight down, they come out to these angles here, 20 degrees. And then you're told that the strings have a length of 12 centimeters. And what you're looking for is you're trying to find the mass of these two spheres. And so the first thing we did, and so I'll just go ahead and do it here, so if you haven't done this, think about this, but the first question I asked myself, this is going to be a force problem, similar to a 131 problem, how many forces act on the left ball? So think about this. Okay, hopefully you got 3. And so if I draw the picture of the left ball, again, those 3 forces are the tension, and then mg, and then this new force, which is the 132 stuff, the electric force. It's always good to draw your sort of picture of the force, your free body diagram first. All right, so we have that, and then the other thing we did is what is the correct expression for the force pulling up on the left ball? So think about this here, and again, if you look at our picture, it'll just be this here. So there's the tension this way, mg downwards, and then our force of electric. So pause this if you haven't done this already and think about it, and let me know what you think. Okay, so hopefully you got t cosine of 20. If we look in our picture here, the 20-degree angle is right here. And so if I take this picture, there's different ways to sort of think about it. And in fact, I'm going to take this and erase it just so it's a little clearer what I'm trying to get at. And so we can take this. And so what we want to do is we want to break it into our 2 components. And now the angle we're given, this angle here, so we're told that this is the angle that's 20 degrees. Well, that means that this one in here is the 20 degrees as well. And so this thing here is my tension, and so this one over here would be tension sine 20 degrees, and then the one we're looking for, the one pulling up, would be tension cosine of 20 degrees. Just like we got there. So I'll definitely stop and make sure this makes sense to you. These angles are some of the the trickiest part, I think, of these kind of force problems, and probably the part that you haven't done in a while, so you might be kind of rusty, but make sure this makes sense to you. And then finally, what we want to do is go through and solve for the rest of this problem. And so we have our free body diagram, and the way I would draw my free body diagram at this point would be like this here. So I'd say here I've got the force electric, and then we got the mg. So those two we know. And then what I like to do is take that force of the tension and then sort of treat it as 2 different forces. So upwards we got the tension of cosine 20, and going this way we got the tension of sine 20. And I'll use, which I almost always will, the sort of traditional x, y, x going up and then y going to the right. And so what I'll do is I'll sort of look at our problem in the x and the y direction. Now this thing is at equilibrium, has no acceleration, so what we can do is just say that these 2 forces are equal. So in the x direction I can say that the t sine 20 equals the force electric, and then I can also say in the y that t cosine 20, okay, that upwards force has to exactly balance out mg. Okay, and so you can think about this as sometimes they call it a static problem, but these are our equations. And this is the point where basically our physics is over. So we've written out our forces, and we know that in order for this thing not to be accelerating, these forces have to equal each other. And now we want to go through and solve for what we want to solve for. And I think here again we were trying to solve for the mass. And so lots of ways to do this. I think perhaps the one way to do it is to over here solve this tension, this one right here. So go ahead and solve that and say that t equals mg divided by cosine of 20, and then take that tension and plug it into this equation over here. And so I would have mg cosine of 20 times sine 20 equals force electric. So I basically solved for this tension to isolate it, and then plugged it back in over here because I don't really care about the tension, so let's get rid of it. And I plugged it into this equation and got like this right here. And then one way to clean that up is just to say it's mg tangent of 20. So So that just makes that equation a little bit nicer. And now finally, what we can go through is go ahead and solve for this mass. Okay, so the mass would be, if I solve for that, the electric force divided by G tangent of 20. And now we actually get to the physics 132 stuff. And so if you look here, we've got this equation, and so I'm going to plug in our equation for the force electric. So it's kq squared, and then down here I'm going to have r squared. And of course it's also times G tangent 20. So we basically know all of this except for the r. What is the r? Well, the r is the distance between our two charges. So I would call that the r. Right? And so if we just sort of blow that triangle up a little bit, it's going to look something kind of like this. Now we're told that this side is 0.12 meters and that this angle is 20 degrees. And so this side over here would turn out to be 0.12 times sine of 20. And that's just one side of it. Again, we're just using the trigonometry here, and so our total r is going to be 0.12 sine 20, that whole thing times 2. Okay, so you calculate that and put that over here, r squared, you got the k, the q squared, g tangent of 20, and when I plugged everything in, I got 3.37 times 10 to the negative 6 kilograms. So go through and make sure that that comes out. But again, this will happen sometimes during the semester that you have a problem that's really, you need a lot of stuff from, or some stuff from 131.